Welcome back to the today's class on advanced switchgear. Today we are going to see about restriking voltage transient and its derivation. Electrical power system is an oscillatory network. We know that in an electrical power system, lot of complex circuits and lot of components, lot of machines are connected in it. So the power system will looks like a complex circuit. It is logical to expect that the interruption of all current give rise to transient. Since large amount of machines and large amount of devices are connected in a power system, we know that this power system has an oscillatory network. So while interrupting the power system, the transient will occur due to the large devices and machines connected in it. The transient frequencies depends on the constant of circuit. In a power system, we know the devices are connected in it. These devices have inbuilt resistance, capacitance and inductance. These resistance, capacitance and inductance are known as constants of a circuit. These overall parameters in the power system produces transient frequencies when interrupting a power system using a circuit breaker. Consider a simple circuit having a circuit breaker as illustrated in the figure. You can see a bus bar is present in the power system, and this bus bar is fed by a generating station, and this bus bar is connected to a step-up transformer, and from the step-up transformer a circuit breaker is connected. After that, a long transmission line follows. So a generating station is generating power and feeding power into the bus bar, and this bus bar in turn provides the power to the transformer, and this step-up transformer is used to distribute the power in a long transmission line. So if any faults occurs in the transmission line, or if we need to switch off the transmission line, we need a circuit breaker after the step up transformer. So a circuit breaker is placed between the transformer and the transmission line. As represented in the figure, the transmission line has a phase fault or phase to ground fault in the feeder. A short circuit occurs on the feeder very close to the bus bar. This figure represents the circuit diagram of the previous line diagram. You can see the generator which is feeding the bus bar, and its voltage V equal to V max sin omega t. Okay, this alternator is generating a voltage of V, and this voltage is fed into the power system through the inductance and the resistance and a capacitance. After that, a circuit breaker is present. After the circuit breaker, you can see a short circuit fault occurs in a transmission line. So what are these inductance, resistance and capacitance? Let L be the inductance per phase of the system up to the fault point. You can see the fault has occurred in the transmission line. Since the fault is present in the long transmission line, the inductance of the transmission line is calculated up to the fault point. After the fault, the inductance is not calculated or considered. We know since the transformer and generators are wound using coils, then these coils will possess inductance in nature, and these inductive effects are lumped together as a inductance L and shown in this circuit diagram. Let R be the resistance per phase of the system up to the point. Since the resistance is present in the transmission line and the coils of the transformer and the generator, we can say the resistance R per phase of the system up to the fault point is shown in the circuit diagram. Let C be the capacitance to earth of the circuit breaker porcelain bushing. Since the capacitance is present in the long transmission line and also in the circuit breaker porcelain bushing, this capacitance is inserted in parallel, whereas the inductance and resistance are inserted in series with the generator. Consider opening of a circuit breaker under fault condition. Now the circuit breaker is opening due to a short circuit fault occurring in the transmission line. Before current interruption, the capacitance C is short circuited by the fault, because if the fault occurs in the transmission line, at once the capacitor present over here gets short circuited through the fault, so the capacitor voltage and current drains through the short circuit path which is created by the fault. Short circuit current through the breaker is limited by resistance R and inductance L. Since the generator is producing the supply and feeding the long transmission line through the inductance and resistance, after that the capacitance is connected. Since this capacitance is after the inductance and resistance, so the short circuit current which is flowing passes through the inductor and resistor. So the resistance and inductance has an effect on short circuit current. When a short circuit occurs, these inductance and resistance will limit the short circuit current flowing through the fault. Resistance R is negligible compared to inductance L. Since the transmission line composed of inductance more than resistance, so the resistance is negligible and it can be neglected. The short circuit current I will lag behind the system voltage V by 90 degree as illustrated in the figure. You can see in this figure, this is the x-axis which is the timing axis, and in the y-axis represents two quantities. One is the short circuit current I and the other one is the system voltage represented in dashed line. From this figure you can notice that when the system voltage is 0 at this point, the current which is lagging behind the voltage. So since we are having inductance as a predominant one, the current which is occurring during a short circuit of a power system is of inductive in nature, and this current lags behind the voltage by 90 degree. With contacts opened and the arc broken, current I is diverted through the capacitance C. You can notice that this point the contacts of the circuit breaker starts to separate, and at this point you can see the voltage across the circuit breaker is diverted and the current is also interrupted. So a maximum voltage of 2V max will appear across the both capacitor and also across the circuit breaker contact. So the voltage V has been for effective only across the inductance L is suddenly applied to the inductance L and capacitance C in series. We know that since from the previous figure you can see resistance and inductance are limiting the short circuit current. Since the circuit breaker has opened the short circuit fault, the maximum voltage of 2V max will be applied across the circuit breaker contacts, and this high value of voltage creates a transient response because the voltages and the currents are diverted into the inductance L and into the capacitance C, which are connected in series. So we know that if inductance and capacitance are connected in series and the alternating supply is feed into it, at once the circuit becomes oscillatory in nature. So this oscillations is created by the inductance and capacitance which are present in the power system. So these peak restriking voltages will occur and this peak value will be up to 2V max. This forms an oscillatory circuit having a natural frequency Fn equal to 1 by 2 pi square root of 1 by LCH. These restriking voltage transient frequencies will be having a natural frequency of the system which will be equated into a equation in a way that 1 by 2 pi into square root of 1 by amount of inductance L and the amount of capacitance C present in the power system circuit. So these two are the variables. So these two variables creates the natural frequency Fn, and which in turn makes the peak restriking voltage and the restriking voltage to get oscillate in its natural frequency. Initial charging current surge tends to carry the voltage across the capacitor C and therefore across the circuit breaker contacts to double its equilibrium value. Since the charging current surge carry the voltage into the capacitance C, at this point the circuit breaker starts to open, so this equilibrium value gets doubled, so only we are getting 2V max. The restriking voltage transient gets a maximum voltage of 2 into Vmax. This occurs because of the equilibrium value gets doubled due to the charging current surge and also due to the capacitor and also due to the separation of two contact plates in the circuit breaker to clear the fault at that time. This voltage frequency will be of the order of 10 Hz to 10 kHz depending on the value of inductance and capacitance present in the power system. So the restriking voltage transient frequencies depends on the value of inductance and capacitance present in the power system, and this value is of the order of 10 Hz to 10 kHz. So while interrupting a huge or large transmission line, At once, a very high transient will created with a restriking voltage of 2V max, which depends on the system voltage, and a frequency will depends up to the inductance and capacitance present in the long transmission line plus the devices connected in the power system. The actual power system composed of distributed capacitances and inductance. On seeing a power system in a real time, these power systems have capacitances distributed and inductance distributed in nature. So, these inductance and capacitance of a power system cannot be lumped together for a particular fault in a particular location, because these capacitance and inductance are distributed all over the power system in a uniform manner, or it also may vary. Power system configuration is very complex and difficult to imagine, since the power system configurations which are seen earlier is of very simple form of a line diagram, but in normal these power system configuration cannot be imagined because it will be very complex, and this complex power system cannot be imagined by a human. For example, you can take your town and see your house, your neighbor house and his neighbor's house all are connected to a single post in a street. So on a single street you can see lot of houses connected to the same post, and inside your houses lot of devices are connected. Similarly, in your neighbor's house also lot of devices will be connected. Similarly, in his neighbor's house also lot of devices will be connected. So all these devices are connected into the power system in your area. Similarly, there will be a lot of areas and lot of streets in your city. So this complete power system has to cover all the streets and all the villages and everything. So you cannot imagine a power system. It is very difficult to imagine, and it is a very complex one. Restriking voltage transients of circuits have several component frequencies ranging from Hz to kHz. Since this very complex and very difficult to imagine power system has not only single component of frequency, it will have several components of frequencies ranging from Hz to several kHz. Expression for restriking voltage transient. The circuit breaker contacts are opened and the arc finally gets extinguishes at some current zero. A voltage V is suddenly applied across capacitor C and so across the circuit breaker contacts. This we have seen earlier how these effects has occurred. The current I which flows to the fault is injected in the capacitance C and inductance L. So we can take the total fault current I is equal to IL plus IC, which is the inductance current plus the capacitance current. Then we can transform this equation into I is equal to 1 by L integration of V dt plus C dV by dt. Differentiating this equation, we get di by dt is equal to V by L plus C d square V by dt square. Assuming current 0 time flows through the circuit breaker contacts when T is equal to 0, we can say that the voltage across the circuit breaker contacts V will be equal to V max into cos omega t. Similarly, the fault current flowing through the circuit breaker contacts can be assumed as I is equal to V max divided by omega L sin omega t before opening the contacts of the circuit breaker. On differentiating this equation, we get di by dt equal to V max by omega L into omega into cos omega t. At time equal to 0, modulus of di by dt equal to V max by L. So this is the second equation. Substituting equation 2 in equation 1, we get V max by L equal to V by L plus C d square V by dt square. The solution of the standard equation is of the form. By using mathematical standard equations form, we have simplified this equation into V is equal to V max 1 minus cos t by root of LC. V is equal to V max 1 minus cos 2 by Fn t, whereas 1 by LC, 1 by root of LC is converted into 2 by Fn, which is nothing but omega. From equation Fn equal to 1 by 2 pi square root of 1 by LC. Square root of 1 by LC equal to 2 pi Fn equal to omega n. This expression is for restriking voltage, where Vmax is the peak value of recovery voltage across phase to neutral, T is the start time in seconds, and L is the inductance in Henry, C is the capacitance in Farad, and V is the restriking voltage in volts. The maximum value of restriking voltage is equal to 2 Vmax, and it occurs at a time interval t is equal to pi by omega, where omega is equal to 2 pi f, and we can simplify this equation into pi into square root of LC, where L is the inductance of the complete power system and C is the capacitance present in the power system. So these two quantities are creating the time varying variable T, which decides the frequency of the oscillation, and the maximum restriking voltage will be equal to 2 into Vmax. Thank you.